Thank you very much. So thanks for the introduction, and a special thank you to the organizers. So you go around, you speak at a lot of conferences, and you can really tell when they put a personal touch on things. They've been extremely hospitable, and I'm very grateful, not just for the introduction and the opportunity to speak here, but also for the extreme hospitality that you've shown. I'm going to talk to you today about something that I think is very important. It's a talk that I've given several times over the past several years, but I keep making it the talk that I give at conferences like this because I think it's very important. It's about how a Bayesian should be thinking about big data. There's an algorithm that I call the consensus Monte Carlo algorithm that'll be the star of the show. I have other people to thank, and these are my co-authors on the Consensus Monte Carlo paper, which was just published in some special issue somewhere, and also several people that have talked to me about this problem with helpful conversations. David Draper, Nick Polson, and in particular, even though he's not here today, Gilberto Lopez, who helped with some of the new stuff that I hope to get to at the end of the talk. The outline of the talk goes like this. I wanted to start off with some introductory material on big data, why Bayesian ideas are important for big data, and the importance of cloud computing. Part of this is going to be, I'll try to keep this as short as I can, but I want to, as part of the introductory remarks, convince you that there's an actual problem. And the main problem that we have is that when you have a very, very large data set, so large that it can't fit on a single computer, you need to have multiple computers solve the problem. When you have multiple computers working together, they have to talk to each other. Talking to each other takes a long time. And so I've got a little example showing how long that can take, and how it's in the type of cloud infrastructure that we have at Google, absolutely vital that we have an algorithm where we minimize the communication between machines. Consensus Monte Carlo is the algorithm that does that computation where you don't have to have the machines talk to each other very much. And then I'll show a bunch of examples of applying Consensus Monte Carlo to a couple of different problems. There's some new work, it's still very preliminary, that I will hope to get to at the end of the talk, which is when my normal Consensus Monte Carlo trick of just averaging things doesn't work, and then we'll conclude. Okay, so we've been living in the era of big data for a few years now, and there's some concern out there in the world that the term is overhyped. And one of my pieces of evidence that the term big data is really starting to get a little bit too hot is if you turn on the radio, at least in the United States, you can turn on the radio and you'll hear a music band play called Big Data. And they don't have anything to do with big data, right? They're not statisticians, they're just guys that look like this that play music. And I guess their song is called Dangerous, which, I don't know if that's something to be worried about for big data or not. If you were concerned that the term was overhyped, you might hire a consultant to tell you just how overhyped it was. There's a consulting firm out there called Gartner Research, and they have a thing called the hype cycle, which they use to track their view of various different buzzwords that are floating around in the tech industry. So this is the Gartner hype cycle as of 2014. This is a consultant's graph, so the axes really don't mean anything. But on one axis you have their expectations, and the other axis you have time. Big data, and they have this thing chopped up into several different zones here. So they've got innovation trigger, which I don't know what that means. And then here we have the peak of inflated expectations. And we can see that big data is right here on the graph. It's past the peak of inflated expectations, and it's on its way to the trough of disillusionment here. After spending some time where people are disappointed with big data, that it'll reach the slope of enlightenment and finally the plateau of productivity. So I guess what this means is if you believe Gartner, then big data is sort of on its way down this slope, which is kind of good news because you don't have to force the term big data into your grant proposals and abstracts anymore. All right. The big data world has been with us for a long time, but there's one particular event that I think was very important for making it the phenomenon that it has been for the past decade or so, and that's the publication of this paper by Jeff Dean and Sanjay Ghemawat, both at Google. These are the guys that built the Google infrastructure that makes the search engine work and everything like that. In 2004, they published a paper on something called MapReduce, which some of you may have heard of. Some of you may know it by the open source implementation of MapReduce called Hadoop. MapReduce is a technique for, it's essentially for data processing, right? In embarrassingly parallel problems, what you're able to do is you're able to take your big data and send it out to a bunch of different computers, process it locally on each computer. They call that the map step. And then take the results of your processing and send it to a central repository. That's the reduce step, right? So this is a one and done algorithm, MapReduce, for handling embarrassingly parallel problems. The initial MapReduce allowed you to do this cycle once. There's later updates that allow you to kind of iterate back and forth. But mainly this is a technique for data processing, not necessarily for data modeling. But the key point here, and the reason this is such a big innovation, was it allowed us, or allowed Google to build infrastructure that could handle the internet. Right? Google needs a copy of the internet on its computers. The internet is really, really, really big, right? And so you need an infrastructure for being able to handle data sets that don't fit on a single machine, and this is basically how you do it. All right. In this world, Bayesian ideas haven't really made it as far as they should. And the main reason they haven't made it as far as they should is that there's this meme out there that Bayesian inference doesn't scale. How do you do Bayes? Well, you do MCMC, right? MCMC is slow, right? At least that's the thought. But regardless of how you do the computing for Bayes, the Bayesian ideas are important in big data problems for exactly the same reason they're important for small data problems, right? In Bayesian models, you can make better predictions by averaging over a bunch of different models, a bunch of different parameterizations or different models. You can do better by doing that averaging than you can by just choosing the model that looks best according to some criterion, right? So you can make better predictions. It turns out that uncertainty quantification is actually very important in this world as well. And I'll get to that in a second. And finally, big data problems, oftentimes you can think of big data problems as big collections of small data problems. So at Google, I guess the main Google product is the search engine, and the main way the search engine makes money is by showing people ads, right? So really what I want to know is when I see someone search for talks on big data or whatever you're searching for, which ad should I show them, right? And if you search using a search term that I haven't seen before, then I don't necessarily have a big data problem. I've got a small data problem, right? For that particular search term, I need to know which ad is going to do well. If I've seen that search term a bunch, and I have a bunch of historical data on which ads do well, then okay, that's a big data problem. But if people come up with new search terms all the time, and so when I'm trying to figure out which ads to show people, well, then I don't necessarily have a big data problem. I've got a small data problem for that particular search term, and I need to pool information from closely related search terms. So ideas like hierarchical modeling and things like that are very important. But of these three, the one that I really want to highlight is the problem of uncertainty, right? So we sort of intuitively understand that uncertainty is an important issue, but sometimes it's hard for us to articulate why it's important. Intellectually, well, obviously you would want to know how sure you are about something, but it's hard for other decision makers to understand why that's important. In Silicon Valley, it's particularly important because the computers that run these algorithms that Google and Amazon and Facebook are all built upon, they're fitting models over and over and over again, right? So they've got a big logistic regression or something like that that says, given this search term, the probability that you would click on this ad is 0.000 something, right? Well, where does the data come in order for us to fit those models? Well, it's observational data. It's data that comes from me watching people search on Google, right? Some fraction of the time in the past when I showed this search term, I showed this ad and it got clicked. So I have an empirical estimate of the click rate for that ad. But of course, there's a feedback loop here because the reason I saw that training data in order to fit that model was because last week's model said that that was the right the right ad to show you for that search term, right? So the model is not only fit to observational data, but it's fit to observational data that was produced the last time that I fit the model, right? Which is there's a feedback loop there that might make you a little bit uncomfortable. And so how do you break that feedback loop? Well, we'd like to be able to fit these models to experimental data, right? But I don't want to run a fresh experiment every week in order to figure out, refit the search engine or refit the ad engine, right? I need to be able to experiment intelligently, right? So how would I do that? Well, one way to experiment intelligently is to think about an ad that is probably pretty good, but maybe isn't the best ad, right? And instead of flipping a coin that randomizes among all the ads that I could possibly show you, I'd like to flip a coin that randomizes among the ads that might be near the top, right? And so uncertainty is really critical for that. And this is just a little bit of an aside. There's a whole nother talk that, that this would go into if we wanted to explore this idea in detail. But really the thing that drives Silicon Valley, or I think should be driving Silicon Valley, is an example of what's known as the multi-arm bandit problem. The multi-arm bandit problem is a very old problem in sequential experimental design, right, which is kind of what we have here. We need to figure out, without annoying everybody, a way to conduct an experiment so that we can learn what the right ad is to show with each search result and which search results are the right search results. So you can think about this as entering a Las Vegas casino, and there's a row of slot machines there, right? Each slot machine, think about it as conceptually as an ad that I might show that goes along with a particular search term. And I need to figure out which one of those is the best one. The only way for me to do that is by trying several of them and seeing which ones work, right? An experimental approach, right? And there's a fundamental trade-off here between trying to show ads that my model says are the relevant ads and exploring the space of other ads in case I'm wrong, right? So that sort of ought to make you think, well, that sure does sound like it's a Bayesian problem, right? Because I'm unsure about which ad is the right one, right? To the degree that I am positive that this ad is the right ad, I would never do anything else, right? So there's a model here that kind of relates the outcomes, the clicks or the no clicks, to the parameters of my model, right? If I knew what the parameters of my model were, I would know which ad to show, right? Because my model would tell me, right? But if I'm not sure about my model, then I'm not sure which ad to show, and I need to kind of balance this trade-off between exploration and exploitation. Well, there's an algorithm that was invented actually back in the 1930s called Thompson sampling. And in the 1930s, the problem was much simpler, but the basic heuristic here says that what I should do is I should look among my spaces of all the ads that I would consider showing, right? List them out, ad number 1, ad number 2, ad number 3, right? And compute the posterior probability that each one of my ads was the best one, right? So what's the probability that ad 1 has the highest click rate, for example? And then if ad 3 has a 72% chance of being the best ad, it should have a 72% chance of being the thing that I show you. That's the Thompson sampling heuristic. And so this is a gross simplification of the problem that we have, but it sort of, I hope, gets the idea across. And how do we break this cycle of this feedback loop? Well, we'd like to inject a little bit of experimentation into the world. This Thompson sampling, which uses this Bayesian uncertainty quantification as an input, is the way to go. All right. So Bayesian ideas are really, really important in these big data problems, in particular, the big data problems that we have at Google. So what have Bayesians been up to? Well, with a few exceptions, when at least the papers that have come to me to review, when Bayesians talk about doing big data, they're thinking about data that fits on their laptop, but is too big for their MCMC to work well, right? And so that's what we've been calling big data. That's not what the rest of the world is calling big data, right? These guys sort of define the problem. This is what big data is. They're the big data guys. And I think if we're going to use their words, we should try to solve their problem, right? Now, the work that we've been doing in the Bayesian community is useful and welcome and good, but we haven't really been focused on size as much as we've been focused on speed, right? If we can make our Monte Carlo or whatever go faster, or learning algorithms go faster, then we can handle big data. Well, that's only true if your bottleneck is processor, right? If your bottleneck is memory or disk or something like that, then I don't care how fast your algorithm is, it's not going to be able to fit a model based on data that it can't see because it's not on your machine, right? So there's several different approaches that have all, I think, been amazingly successful. So, you know, Mike's work with Mark Suchard on GPU computing has been really fantastically amazing. It's hard to do, I think. I mean, you have to program the GPU in a different way than you program your CPU. So there's some challenges there. There's some other people in the room that have been working on what I call data-friendly Metropolis Hastings algorithms, where you subsample the data and you sort of look based on your subsample and make a prediction about whether, if I were to look at the full data, would this proposal be accepted or not, right? So you don't necessarily have to loop through the full data every iteration, but you still need access to the full data on your computer so you can do the subsampling. And then variational Bayes is very popular, particularly in the machine learning world. I sort of think that, you know, a lot of these guys will tell you that, you know, if they could do MCMC or Monte Carlo computations, then they would. But they can't because it's too expensive. So in all of these cases, I think that they're solving an important problem, but they're not necessarily solving the big data problem. And the way you solve big data, which is, you know, you have a data set that's too big to fit on a single machine, is, well, you have to have multiple machines. And in Silicon Valley, this is what that looks like. So here's some pictures just taken off the internet for if you search for pictures of a data center, this is what data centers look like. They're gigantic warehouses full of computers, right? Larger than any building on your university. They're constructed specifically to handle the issues of the heat that would come from all these different computers and the information flow and the energy that it takes to run one of these things, which might have, I don't know, 100,000 computers in it or something like that. And, you know, Google has several of these throughout the world, and so does Amazon, and so does Microsoft, right? And, you know, if this is your computer, then all of a sudden you don't have a processor bottleneck anymore, and you don't have a memory or disk bottleneck anymore. Right? And somebody else has to, you know, somebody else is charged with making sure this thing runs. You're not your own system administrator. But, you know, that's all well and good, but, you know, if you don't work for Google, I mean, am I just up here talking about something that's just for me, or can you play in this world too? And the answer is, of course you can, right? Because people are, you know, Google and Amazon and Microsoft and a couple other folks, I guess, are in the business of renting this stuff out, right? And so the bad news is that costs you money, but the good news is it's really, really, really cheap, right? So here you can't, I'm sure you can't read any of this, but what this is it's a screenshot from the Amazon EC2 page. How much does it cost to rent a computer on EC2? And they have several different computers you can rent, depending on how fast you want the processor to be, how much memory and disk and things like that you want, what your priority is when there's several jobs competing for the same computer. But the cheapest one that you can get costs slightly under 1 cent per hour, right? And I want you to think about that and think about how much it costs you to get a work study to work on your problem, right? So if something costs you 1 cent per hour, and you need 1,000 computers to solve your problem, right? You could probably solve your problem in an hour if you had 1,000 computers working on it. That's $10, right? So it costs you money to play in the big data space, but it doesn't cost you much, right? It costs you less than a work study. So here's the corresponding page for Google. Again, there's several different configurations. These don't necessarily correspond to the same configurations you can get from Amazon. The Google number, the minimum number on this slide, is 1.5 cents. So if you buy your computer from Google for an hour, 1,000 of those will cost you $15 instead of $10, right? So we're still not breaking the bank here. So in order to kind of use the techniques that I'm talking about and actually solve big data problems, it does cost a little bit of money, but it's so cheap, even an academic can do it, right? Okay, so then the question is, now that we have access to these large computers, how do we use them, right? How do we solve this, how do we use our infinitely big computer to solve a big data problem? Here's an example of the type of experiment that I was mentioning before, the multi-arm bandit experiment that I want to run. This is something that I encountered very early in my time at Google, but it was very instructive to me. There's a group at Google that makes these ads, right? And so if you go to a third-party website like the New York Times or ESPN or something like that, then you'll find a little section of advertisements. And those advertisements are put there by third-party ad networks. Google has one. And so you'll see here it says, actually here, ads by Google. In that part of the ad is what it says. And I'm showing two examples here. One is the New York Times, which is gets a whole lot of traffic, right? A lot of people go to the New York Times. And then there's another website over here called howtobuystuff.com, right? And raise your hand if you've ever been on howtobuystuff.com. No hands go up, right? So I think howtobuystuff.com gets a much lower traffic, the throughput, than the New York Times does, right? And howtobuystuff.com is formatted differently than the New York Times is. New York Times has a white background with a black font. It's got a particular, probably the Times is the font here. They'll have a different font over here. And the ads look different, right? Here, the ad for the New York Times has a gray background with a gray bar on top. Over here, the ad for howtobuystuff.com is actually a picture, right? But the format of these ads turns out to be a really important thing, right? Getting the right shade of blue or gray on one of these things, particularly if it's different than the shade of blue or gray you showed last week, can impact the success metric of one of these ads by 5% or something like that. It'll be 5% better with the right shade of blue than with the wrong shade of blue. If you compare that to getting the right machine learning to figure out which of these ads to show, that's something that it's a big victory if you get 1%, right? So, which is dispiriting for the mathematicians, right? Getting the right shade of blue is more important than getting the right algorithm, such is life. But okay, so anyway, that's the type of experiment that I'd like to run. And so when I run this experiment, I have the foreground color, the background color, and the font, say. And let me just take 2 or 3 different examples of each of those things, just to kind of get the ball rolling. The ad guys gave me a little data set, some little chunk of a Sunday afternoon or something like that they had. And in that little chunk of time, they had 600,000 internet domains, right? So that's ESPN is an internet domain, nytimes.com is an internet domain, and then there's articles and stories and things like that under each of those domains. So for each one of these things, I want to fit a model, right? And I want to pool information because the New York Times it's got enough data to justify its own experiment. Howtobuystuff.com might need a little help. Right? We might need to pool information from other low traffic sites in order to accurately estimate the model for those guys. So I'll try a very simple hierarchical model, right, where I've got a logistic regression. I'll point with the mouse here. So I've got a logistic regression where each internet domain has its own little logistic regression coefficients. And what are those coefficients multiplying? Well, they're multiplying a set of dummy variables for whether the foreground color is, light gray or dark gray, or the different colors that I'm experimenting with. And so you might think, if I'm just doing a few designs of ads, this X is going to be a very small thing. Think of X as being something like 10 dimensions or something like that, some very small number, but I've got a lot of them. All right. So this is actually an example of a big data model. Right? If we were to stretch out this hierarchical model and do it sort of a standard machine learning way, it would be a logistic regression with 6 million predictor variables, right? Because I've got 6 million of these sort of ad-specific or domain-specific coefficients. But really, we can sort of think about it in a hierarchical model as a whole bunch of 600,000 10-dimensional problems. It's even less than that because we're going to assume that these coefficients came from some prior distribution, which just for simplicity, I'll assume is normal mu sigma, and I'll put a default prior on mu and sigma, right? So sort of a naive model, just to kind of see if we can do this. And so now, how would you fit this model? Well, if you've never done parallel computing before, then there's sort of an obvious thing you would do. Let me take the data from all these different domains and put them out on a bunch of different worker machines, right? And I'll iteratively map and reduce back and forth, right? So the map step will be, okay, machine, go and take draws of the betas for all the domains that you're responsible for, right? And then once you're done with those draws, we'll mail them back to the mothership, a central node, and that central node will take a draw of mu and sigma, and then we'll just iterate back and forth, right? And if you were on a computer that was engineered for low latency communication between nodes, this would be a great algorithm. So if you're on a GPU, right, this is going to go blindingly quick in terms of not necessarily in terms of the mixing, but in terms of how fast you get numbers out of your system, right? But it's going to turn out to work terribly in the cloud, and I'll show you why. Here is a picture where I'm showing the amount of time it took per half iteration. So the map step and the reduce step each count as a super step in this little graph. I ran this twice, once with 500 workers and once with 50 workers. And so you can see that in both cases I end up with a bimodal distribution for how long each little step took, right? The axis down here is the log base 10 of the number of milliseconds, which, the data came to me as milliseconds. I took the log. I should have rescaled this to be log seconds. But so this 2 down here is a step that took 1/10 of a second. 3 is a step that took 1 second. 4 is a step that took 10 seconds. And 5 is a step that took, 100 seconds, a minute and a half. Right? So if a computer died or something like that, then you might get an example out here. Or if I got booted off and I needed a new machine to come in and take its place. So you can see that in both cases there's a bimodal distribution, right? When I have when I've got 50 workers, then each worker is processing a relatively large amount of data. And so this mode in the distribution over here is the step where workers are taking draws of beta. And this mode over here is the step where the mothership is taking draws of mu's and sigmas, right? And so it's no surprise that when I increase the number of workers tenfold, this mode moves to the left, quite significantly, right? Because each worker has less work to do, right? What is a surprise to a lot of people is that this mode over here actually moves to the right. It takes longer to draw mu and sigma in the 500 worker machine environment than it does in the 50 machine environment. And if you think about that, that's kind of crazy, right? Actually, if you think about it, all of these numbers are kind of crazy because if you look and actually calculate based on timing your C++ code, how long does it take to draw a 10-dimensional normal inverse Wishart, it takes on the order of microseconds, not milliseconds, right? Really drawing mu and sigma is something that is basically free, right? And yet this is telling me it's taking somewhere between 1/10 and 1/4 of a second, right? So it's actually not, the overall step is taking me a long time, but it's not taking a long time because it's doing useful work that I want it to do. And this is really disheartening. So if you take a line straight down from this mode and you sort of figure out what is this number, it's around 1/4 of a second. And it's 1/4 of a second of completely wasted time, right? And this time is not wasted because I'm a bad computer programmer, right? I had the world's best C++ programmers helping me on this project, right? The time is essentially wasted because there's 500 machines and they're all waiting for the last machine to be done before they take the next step, right? It's not wasted because data is moving back and forth along wires or anything like that. It's really no place that we can optimize. It's fundamental overhead of using this shared system. And that's really kind of devastating for an algorithm that needs to communicate back and forth, right? The way that you would on an HPC or a GPU. And what it means is that if I get half of a second per half step of this algorithm, I'm going to get at most 2 iterations per second done here, right? Which was fine in 1992, right? But nowadays, if I'm not getting several hundred iterations done every second, then I sort of feel like I'm wasting my time. So we end up in a place that I think of as the MapReduce paradox, right? So we started off compute constrained, so we parallelized in order to fit our data on many, many different machines, but each of my machines ended up using 0% of its capacity. It's not doing any useful work. So we need an algorithm that will allow us to do Bayesian computation without this massive overhead of communication between machines. This is the consensus Monte Carlo idea. What I'm going to do is, like before, I'll take my data and I'll break it into chunks, right? And at Google, and I think, and this is a term of art, beyond Google, we call these chunks shards. Like you break your glass and it breaks into a bunch of shards. I'll run a separate Monte Carlo, an MCMC or whatever your favorite Monte Carlo algorithm is, on each worker level shard. So P of theta given just the chunk of data that machine knows about. Right. And then at the end of the day, I'll have a bunch of draws from you, and a bunch of draws from you, and a bunch of draws from you, and I'll need to combine them back together. So to get the total posterior given all the data, right? And this is an idea that really ought to work because the mathematics behind it look like this. I mean, so the true posterior distribution for lots and lots and lots of problems looks like this. I've got a prior distribution times a likelihood, and the likelihood is something that factors across. It's a big product of contributions, right? There's an assumption of conditional independence there. So really, if you guys, instead of returning draws to me, all you different machines out there in the audience, instead of returning draws to me, if you would return the math object, the actual function, well, I can compute the posterior just by multiplying those functions together, right? So mathematically, this is an idea that really ought to work. And if we can get it working, it's wonderful, right? Because In this setup, each machine is running completely independently of the other machines. I don't need to worry about some of the nasty stuff that I have to worry about if I'm writing multi-threaded code. There's no race conditions here, right? I don't need to use even really optimized code. I can use kind of my old cruddy R code on each one of my machines. I don't have to be super smart. And if it works in this kind of hostile computing environment that I'm talking about, where communication is really expensive, well, then it'll work in other environments too. So it could work on a GPU or an HPC or whatever, but wouldn't necessarily have to. The bad news is if my conditional independence assumption that I made there is violated, then we would maybe miss some a big time series problem like Emily was talking about. I might miss something where I broke the data to pieces. All right. I think I'm going to run short of time, so I'll go through this really quickly. You need to do something about the prior distribution to share it evenly among the different worker machines. So what I'm going to propose doing, and there are other things you could do, is just to take the information in the prior and break it up. If you have capital S computers, break the prior up into capital S pieces and divide it up equally. There's other stuff you can do. And then how do you form the consensus? Well, again, there's several things that have been proposed. My favorite way of doing it is to say, okay, machine 1, I'm going to take your draw 1. Machine 2, I'm going to take your draw 1. Machine 3, I'm going to take your draw 1. And let me just average all those draw 1s. And I'll do the same thing for draw 2s and draw 3s. Right? So I'll end up with a consensus draw 1, and a consensus draw 2, and a consensus draw 3. And my claim is that looks an awful lot like the draw 1 and draw 2 and draw 3 that I would have gotten had I done this on a single machine. And let me show you why that works, right? If our posterior distributions, if our worker level posterior distributions on each machine had actually been Gaussian, right? And large sample theory is sort of in regular problems, that'll be roughly true. If those, if my worker level machines had been Gaussian, it turns out that taking averages of draws, weighted averages of draws, is going to get me exactly the right answer. So this is a little homework problem for you guys to kind of do, during the coffee break or something. I guess we don't have any more coffee breaks, so after the conference is over, you can do this. But so I've got P1 and P2 are normal distributions, right? And you guys know, if they're normal distributions, how to multiply P1 and P2 together and figure out what that distribution looks like. If we call one of these things the prior and one of them the likelihood, then the math starts looking really familiar, right? So if Z is P1, if Z is distributed according to P1 times P2, then Z is again going to be normal, and the mean is going to be a precision weighted average of the means, and the precision is going to be the sum of the two precisions, right? So now take X according to drawn according to P1 and Y drawn according to P2, and take W1, which is the precision from P1, and W2, which is the precision from P2, rescaled so that they're weights. Take this weighted average, and you'll see that it has this mean and this variance. So just do the moment calculation yourself, and you'll see that that's true, okay? And what that says is that if my worker level posteriors were in fact Gaussian distributions, then taking weighted averages of the draws is going to get me a draw from the joint posterior, which is great, right? If things are Gaussian. Now, in order to do this, I need to know what the weights are, but that's okay because I have a full Monte Carlo from each one of these guys, right? And so I can just calculate the variance. The sample variance from machine 1 and the sample variance from machine 2 will give me invert those, and I'll end up with something proportional to the weights that I need. So that's kind of cool. So I'm going to spend a few minutes here going through some examples of what happens and a few examples that I've tried where things are non-Gaussian, right? Because I want to see if we can break this thing. Turns out you can break it, but the point I'm going to try and make here is that even though you can break this, it's remarkably robust. So here's an example. Here's a big data problem. Not really, but so I've got 1,000 Bernoulli trials, right? It's my big data. I've got 1 success and 999 failures. That's my data set. And I want to break this data set up among 100 different workers, right? And so what I'll do is I've got 99 workers that see all failures, and I've got 1 worker that sees 1 success and 9 failures, okay? So I've got 100 different beta distributions, and drawing from 100 different beta distributions, I'm going to average them, okay? I'm also going to do the same thing, take draws from the right beta distribution on a single machine that has my 1,000 Bernoulli outcomes. The single machine posterior is this solid black line right here, right, which you'll observe is highly skewed and non-Gaussian, right? My thing that I get from averaging across 100 workers is this dotted line right here, which you'll, I think, agree looks an awful lot like the solid black line, okay? So I've got an algorithm that was optimal if my worker level posteriors were non-Gaussian. I'm taking that procedure that was inspired by the Gaussian theory and applying it where Gaussian, things are clearly non-Gaussian, and I still managed to capture relevant features of the posterior distribution. There's this really heavy skewness that I'm able to pick up, right? If I had just assumed that things were Gaussian and done the combination and based on a Gaussian final assumption, I would miss this skewness. It's not perfect. If you do a QQ plot, you can see that we're off in the tails by a little bit, but I've shown this to lots and lots and lots of people, and every time I do, I'm sort of floored by how well it works in this case. All right, let me skip through a couple caveats here and go to the next example. So sticking again with success-failure trials, right? Let me move to logistic regression. I want to show you simulated data, again, where I can compare on a single machine to the consensus Monte Carlo. There's a data set that I'm going to simulate. I'm going to have 5 different predictors. Each one of my predictors is going to be a binary, it's a dummy variable, right? My first predictor is going to be an intercept. It's 1 with frequency 1. It's always 1. My second predictor is going to be 1 20% of the time. Third predictor is going to be 1 30% of the time. X5, my fifth one, is going to be on only 1% of the time. Okay. Here's the logistic regression coefficients that I'm going to use in my simulation, right? When I simulate the data with these x's that I'm going to simulate as well. And you'll notice that my variable, which is on very rarely, actually has a really big logistic regression coefficient. So this is it's an indicator that I typically don't see it very much, but when I do see it, it's a strong signal for success, right? So I'll go and I'll generate 10,000 observations from this simulation, and here's basically the entire data, right? So logistic regression, so I can summarize things in terms of successes and trials, and there's only so many covariate patterns that I can have here, right? So I've got 10,000 observations, and you can see the bottom half of my observations. These are the ones where x5 is equal to 1. Right? I'm going to take these 10,000 observations and I'm going to divide them up among, I think, 100 different workers, right? And so you can certainly see that I've got fewer than 100 observations in a lot of these rows down here, right? And so some of my workers are not going to see, actually most of my workers are not going to see individual covariate patterns there. So some of my workers actually aren't going to see any x5 at all. Here's an example. Here's a picture of what the posterior distribution looks like for the single machine logistic regression algorithm and a couple of different consensus Monte Carlos. What I'm doing is I'm showing the marginal distributions along the diagonal for each of the different coefficients, right? And I'm showing the joint distributions on the off diagonal. On the upper part, what I've done is I've zoomed in to kind of where the meat of the distribution is, right? On the lower part, I've kept everything on a common set of axes, right? So you can kind of get a sense that, the blue is away from everything else, but, on this scale, where we're looking at things on a common set of axes, things are pretty much piled up on top of each other. The different colors represent here, black again represents what I get from the single machine algorithm, which I'm taking to be the right answer. Oops. There's a red, which, when I compute the weights for doing the weighted average, one way for me to compute the weights is by taking the information as we think about information, the matrix version of information, right? I'm weighting by the inverse of the variance matrix. And a big problem inverting all those matrices, I'm imagining, might be hard. I was curious to see how well we would do if we ignored the diagonal elements of that matrix, right? And that's what the green is. And then there was an argument that I was thinking about for a while that said, well, all of these observations are independent a priori, right? They're all coming from me randomly distributing data to the different machines, and so really they have the same sampling distribution. So there's kind of a frequentist argument that says that these things ought to have the same, they do have the same sampling distribution, so they should probably get the same weights, right? Well, that's obviously wrong, and what happens is with that is that some of my workers get to see examples where that rare single variable was turned on, right, multiple times. And those guys can end up estimating the effect of that variable reasonably well. There's going to be some others that didn't see it at all, and those guys are going to just end up taking draws from the prior. So I need to kind of build the weights in there. Okay, running short on time, so let me just, real quick, you can do this with the hierarchical model too. When you do the hierarchical model, the way that you want to think about it is to think about using consensus Monte Carlo in order to draw the hyperparameters, right? So what I'd like to do is get the marginal distribution of the hyperparameters down. Then conditional on the draws of the hyperparameters, I can mail those draws out to my worker machines and then do an embarrassingly parallel trip through the data, second trip through the data in order to get the worker level parameters. And so the worker level parameters don't even need to all be on the same machine. So if I do this, then I can, here's a little graph showing how long it takes to fit this hierarchical model on a big data set. If I have 1, 2, 3, 4, 5, 6 shards where, a shard is a chunk of the big data. After, let's see, number of shards is roughly 30 or so. It takes on the order of 12 hours for the single machine algorithm to produce the number of iterations that we're looking for. But of course, this line is essentially constant here, right? We can keep adding more and more and more machines, and so the amount of time that it takes for us to do the problem with consensus Monte Carlo, it takes a few extra seconds in order to get a few extra 100 machines later on, but we can basically fit a hierarchical model like this, as big as you want in a constant amount of time. We can do non-parametrics as well. So BART is an example of a Bayesian non-parametric model where you have a bunch of trees, right? So I've got a bunch of functions here that, in the case of BART, happen to be trees. You can't really average a tree, right? So, except in some sort of weird math space thing. But what you can do is you can average the draws from the predictive distributions of the trees. So here on the top axis, what I'm doing is I'm showing you the posterior mean for the consensus Monte Carlo versus the single machine algorithm for 30 shards of data on kind of a standard test function that the BART guys like to use. Here's the, so I've got, let's say the single machine algorithm on one axis and then the consensus Monte Carlo on the other one, they line up. Here I'm looking at the lower 2.5% credible interval, they line up, and the upper 2.5% line up. So at least at those spots in the distribution, things work well. Don't worry about the bottom part, because I do want to spend 2 minutes talking about what happens if averaging doesn't work. Right? I've shown you a bunch of examples where we can just average and things are fine. Right? When averaging doesn't work, then what do you do? Well, clearly if your posterior distribution is normal, then averaging is going to, there's a theorem that says it's going to work great, right? But if it's not normal, and there's been several papers out there that have kind of, as I had originally hoped, taken this averaging idea and used it as sort of a straw man and beat up on it. Okay, here's some examples where it doesn't work. Well, if your posterior is non-normal, then you can certainly write it as a mixture of normals, right? And so how does that work? So if machine 1 had a worker level posterior distribution that was written as this mixture of normals, the W time, sum of W time F, where the W is a mixing weight and F is a F1, F2, F3 are different normal distributions. Machine 2 has a mixture of normals, it's pi times G. Then what I really want is draws from P1 times P2, right? Well, P1 times P2, if I take these two things and I multiply them out, I end up with an expression that kind of looks like this guy down here. I can take the WFs on this axis and the pi G's on that axis. I can multiply those two things together, and I end up with this thing right here, which, hey, that looks like a mixture of normals too. It's a bigger mixture of normals. It's got more mixture components in it. And I have to do a little bit of math to figure out kind of what the mixing weights are for these things. It's, the mixing weight's going to be the W1 times the pi 1 times the leftover stuff that you get when you multiply these two things together. So for the students in the room, this is homework problem number 2. Go figure out what the mixing weights are for this sort of thing. But it's relatively straightforward to do. And so I have this algorithm that if you want to do consensus Monte Carlo based on mixtures, then, well, that's nice because we get back to MC again. So mixture consensus Monte Carlo. I can view my mixture of normals as something that I want to sample from. So how do you sample from a mixture of normals? Well, you take a draw from the mixing weights, right? So I'll take a big multinomial draw based on the mixing weights that I just computed. I'll end up right here. This corresponds to row little k, column little m, right? And so the next thing I need to do is take a draw from the product of f little k and g little m, right? And both of those are normal, or approximately normal. Probably not exactly normal, all right, but approximately. And so how do I do that? Well, I guess one thing I could do is I could just, I know what the model says it is, but I'm inspired by the fact that, we fit the original averaging idea was inspired by Gaussian, but applied to non-Gaussian and managed to keep some of the skewness and things. There's a little bit of robustness when you apply to non-Gaussian data. I'd like to keep that robustness here. So instead of just taking a draw from the mean and variance that I get from this guy, what I'll do is I'll go find one of my draws that I got from machine 1 that is allocated to component little k, and take a draw from one of my machine 2 draws that was allocated to component m, and I'll average those two guys. Okay? And so if we can do this, we'll end up with a more robust consensus Monte Carlo thing, and then there's just a couple of examples here. So here's a test case where I've got two normal mixtures here. Here's my machine 1 draws on the left and my machine 2 draws on the right. And if I do the algorithm that I just described to you, then hooray, it works. So that's I think at that point we can probably declare victory on this problem. I mean, there's still a few more details to work out, and I didn't actually show you a real example with that mixture idea. But it's clear to me at this point kind of how the end game to all this works. If we have a model with a fixed dimension of parameters that are a subset of RP, then I think this mixture idea is going to essentially deliver victory, right? So we'll be able to do kind of arbitrarily nasty posteriors and do fine. There's still more work to do. If we have more complex models that have variable dimensions, and I think this trick doesn't work, if we have models that have discrete components, then that's going to be a problem for the mixture of normals thing. But I think it's a sort of a big step forward that if we do this sort of local averaging instead of global averaging based on the mixture idea, then we can sort of do any arbitrarily large big data problem with the type of regular parameters that we're used to thinking about. So thank you very much, and I'll take some questions.
So you asked me 2 questions, so I'll ask you 2 questions. You ran through the last part so quickly that I think I might have missed something, but so we've been doing some experiments with this algorithm in the case of mixture model settings, and so do you have to handle the label switching issue here? Are you handling that? If so, how? With the mixture components between different machines? And then this is still part of the first question, just to clarify, but the other part of it is if you end up with imbalance classes, so in essence, per mini batch or per worker, that you don't have a representative sample of the entire mixture, how that influences the inferences that you're making. And then I can wait for the second question, all right? I'll just throw it out there right now.
We better wait for the second question because I'm going to forget all of the first question
okay. Go ahead.
Keep going. So let's see. Do I have to handle label switching? I did skip a lot of my comments trying to finish up here. So you don't want to kill yourself trying to fit the perfect mixture model here, right? Because we saw in the first part of the talk or the middle part of the talk, we saw that if things are non-Gaussian a little bit, then averaging is still kind of okay. Right?
Yeah, but that's not true in the multimodal setting. So
I'm sorry?
That's not true in the multimodal setting.
That is not, I missed the next word.
True in the multimodal setting. You showed like a heavy-tailed setting, but.
Right, but I'm assuming you're going to fix the multimodal business here, right? So I can have machine 1s and machine 2s that have different modes, right? And you need to fit a mixture on machine 1 that's going to get the modes of that mixture, right? And you have to do the same thing for machine 2 to get the modes of each mixture. But as long as you get the modes of those things, then the local averaging thing is going to put the modes in the right places.
Except if you have, with the label switching issue, unless you correct for that when you do the averaging, you're going to average into something like, let's say you have 2 modes split across the 0, 0 point in 2D. And then one machine labels that 1, 2, and the other one 2, 1, and then you don't fix that, you average, you're going to get something at 0, 0.
So you remember the answer to the way you answered my question was that you didn't care about identifiability because you're just looking at the distribution, you're not trying to call things thing 1 and thing 2. I have the same answer.
But you're averaging though, so how do you?
I'm not going to necessarily fit my mixture of normals using an MCMC, right? So I'm going to fix it using a variational Bayes or an EM or something like that, right?
Sure.
And so I'm going to have one definition of
so
what.
you're saying the per worker thing is not MCMC in the mixture case.
I think it would be a mistake to use MCMC for that. If we did need the perfect mixture, then MCMC would be necessary, right? But because we have this robustness that comes from averaging, I'm willing to kind of throw away a little bit of some of the benefits that MCMC would give you, right? So we'll do sort of a quick and dirty normal mixture decomposition using variational Bayes or EM, and then there might be, you know, conditional on the parameters of that, the bit where you draw the, you know, which variable does this observation correspond to, or which component does it correspond to, right? That part might be necessary, but in terms of just fitting the model, I think you can fit the model and ignore label switching altogether, right? Label switching is a consequence of there could be 500 different ways to describe this data set that we're looking at right here as a mixture of normals, right? Any one of those is fine with me. Right? As long as we have one of the modes of the mixture model, right? Not the mixture model components of the data, but if we have one of those modes of the mixture model, that then it's describing the data. If there was another way to describe the data with a different mixture,
it all comes down to how you're averaging, right? So
the averaging is going to be conditional on the mixture that we fit.
Yeah.
Right.
Okay. Yeah. Okay. Sorry. The second question goes back to one of your first slides, kind of dismissing the subsampling-based methods because all your data have to live on one machine. I was just very confused by that because, I mean, stochastic gradient descent is one of the most commonly used methods out there in the optimization world, and data, you know, don't have to. I think it was going back to the data-friendly MH.
Oh, sure,
point.
right.
Maybe I misunderstood what that was about, but you know, there have been a number of successes using stochastic gradient methods in the context of MCMC. I was just wondering if you could comment more about what your dismissal of those methods was.
I don't necessarily know that I'm dismissing them, but I'm not sure that the stochastic gradient. I haven't seen maybe I haven't seen the same examples that you're talking about. The examples that I've seen where I'm talking about the subsampling, you need access to the full data on each in order to do the subsampling, right?
Okay, we should talk more about it.
Sure.
Okay, I'll ask further questions for the coffee break.